Welcome to the Godot Engine FPS tutorial series version 2. So over the past year plus, I created over 40 tutorial videos about making an FPS in the Godot Engine, and it was okay. Some videos and topics were better than others, but I really want this series to be as good as it can be for you guys. So I had to fix some things. One, in the first version, everything was linear. So you had to do the videos in order, which made jumping into the series much more difficult. Two, videos were short, which made them quick to watch, but also made them really disjointed and a little bit harder to follow. So what's new with version 2? For starters, this first tutorial, the video you're watching, will cover a lot more so that the base project, which is available to download and use for free on my website, will be much more comprehensive. To give you an idea, this is what version 1 covered, and here is version 2. Now, if you want to hear more about how version 2 is going to be different with future videos, I've got a chapter at the end of the video that you can watch. Otherwise, let's make an FPS. So we're working in Godot 4.41 stable. We have some quick setup things to do first. So if you already have a level setup or a prototype level, you can just skip to the next chapter covering the player controller scene. I've created a prototype level scene and saved it in a levels folder. In fact, I'm going to throw up the file system folder structure if you just want to copy that. The prototype level is a Node 3D parent that holds the level geometry, the player controller, which we'll create next, and the world environment. Now, in my levels, I like to keep all of the level geometry in its own Node 3D parent, so I can turn it off and turn it on really easily. Now, for the world environment node, I just created a basic procedural sky setup. I've also created a separate scene entirely for the world environment, so I can just drop that in other levels and then edit everything all at once. Just a little quicker for prototyping stuff. The geometry has a basic floor and a block to use for a crouch check. That's going to happen later on in the video. So the player controller scene is going to house the important parts of our FPS player character, including the player's meshes like weapons, the camera, and player-based scripts like our player state machine. We'll start with a character body 3D node as the parent, a capsule placeholder mesh with a default size of 0.5 as the radius and a 2-meter height. That's roughly the size of a person. And then a collision shape 3D node that will have a capsule shape 3D that matches our mesh instance size. So if you're completely fresh, even to just 3D within the Godot engine, mesh instance 3Ds are just the visual. There's no collision with those things. So we need to add the collision as a separate node. Now you should see your little capsule guy in the editor window, but you won't see anything if you run your game unless you have a camera. We're gonna house our camera 3D inside our player controller, specifically within a camera controller node 3D. I'm also raising the Y position of the camera controller 0.5 meters so it matches the head placement of our player. I like to have the camera 3D and the node that rotates with the mouse separated. Basically, we're only going to rotate the camera controller node, which will also rotate the camera 3D node because it's a child. This is going to allow us to add additional rotation to the camera 3D node later on when we want to add some camera juice. Separating this really allows you to focus the different rotations and then simplifies adding new smaller screen shakes or movement rotations later on. Now, when we add a camera 3D to our player controller scene, it's going to allow us to see when we run the game. But if we want to look around, we're going to need to capture the movement of our mouse. To do that, we're going to add our first component. Now, could you add the mouse capture code into your camera controller script? Yes, but we're going to make a practice of making our code more modular in version 2 so that we don't end up with really long and unorganized scripts. Those really long scripts, they make editing or adding new features harder because things just get really unorganized. Our mouse capture component will have a script focused on only one thing, and that's going to be capturing the movement of the mouse. Then other scripts can get that data when they need it. First, we're going to create a components node to just organize things better, and then a basic node for our mouse capture component. And with that, let's take a look at the mouse capture script. I've given the script a class name. This helps with typecasting and other scripts so that I can get autocompletes and just honestly helps organize things better. I also like to put a debug export variable in scripts like this so that I can easily turn on and off any printing or debug code. I'm also really starting to use the export category option as much as I can to just help organize export variables. And I think it keeps things cleaner. As you get deeper into making a full game, you're going to realize just how unorganized things can get really, really quickly. This organization is just, it slows everything down. So we try to keep it as tidy as possible. The goal of the script is to capture how much the mouse moves vertically and horizontally, which we'll then use to move the camera. The Godot Engine has different mouse modes that include mouse mode captured, which holds the mouse in the center of the screen and then hides the cursor. With the mouse centered, we can check how much it moves relative to the center every single frame. To do this, we use the built-in unhandled input function. This function automatically triggers whenever an unhandled input event occurs. Unhandled here means that it hasn't been used by any other input function or a UI user interface function. Moving the mouse will fire this function. So we check if the input event is truly the movement of the mouse with event is input event mouse motion. And we also check if the mouse mode is our mode captured. This is not so important right now, but when we start to do user interfaces and we need to disable that camera movement, it's going to be super important. If the input event is our mouse moving, we set the X and Y of our mouse input vector to variable. We're using the negative relative movement of the mouse so that it moves the camera in the correct direction and then multiply by our mouse sensitivity. Obviously, higher sensitivity values are going to make the mouse movement higher and the camera is going to move more. In the ready function, we set our mouse mode to our current mouse mode export setting. And we also need to reset the mouse input variable to 0 every frame. Now we do this because we don't want the mouse movement to be cumulative. We want it to reset every frame. If you do cumulative, it's going to move too much. It's not going to work. Let's also test our script with a debug check by printing our mouse input value. We can use our debug boolean as well. Now when you run this, you should see the values change when you move the mouse in the output window. If you don't, make sure you turned on the debug for your script and the inspector tab. And now that we have how much the mouse is moving, let's use that information to look around. We'll need a new script for our camera controller. In it, we set a new class name and a set of export variables. In addition to the regular debug boolean, I like to create a references category for any node references we want to specify manually. Here we'll reference our player controller node. For that, we'll need a new script in our player controller node as well, and then also our mouse capture component node. And obviously don't forget to set those references in the inspector. We're also going to have some camera settings for our camera movement. As the player looks up and down, we want to clamp the camera rotation so that it can only look up so far and only down so far. Otherwise, you're going to end up doing a somersault or a flip, which maybe it's something you're going for. So in that case, don't worry about it. Here, I'm using the export range so that I can specify the values the variables can have. I've set mine to -90 for the lower limit and 90 for the upper limit. These are actually degree values that we need to then convert in our rotation function. We'll need a rotation variable to hold our rotation and a new function, update camera rotation. This function is going to take our mouse input vector 2 and use it to rotate the camera vertically and horizontally depending on the amount of mouse movement. We set our X and Y rotation to our input values. Do note here that the Y input goes to the X value and the X input goes to the Y value. If that sounds really weird to you, it's because we're actually rotating along those axes. X is the one that goes left and right, and therefore it rotates up and down, and then Y goes top to bottom and therefore rotates left and right. That is not a good demonstration. We then clamp our X rotation using our tilt limits, but because we need radians, we need to use the degree to radians function to convert our values. At the very end of our script, we also set our Z rotation to 0. because in this case, we never want to rotate on the Z-axis with the mouse. You could do that for something like a specific effect later on, but that's a no-no here. You're going to make people sick. Now, we do have an issue to solve. If we just rotate our camera with our rotation, the camera's going to look around just fine, but our player's direction is not going to move. So when we look left and right in the FPS, the player's forward direction also changes. So just rotate the player, right? Well, that works for our horizontal movement, but we can't have the player rotating up and down because they're going to like flip around, and that doesn't even make sense. So we can't do that. So we're actually going to split our rotation. We use the Y rotation, our left and right, to rotate the player, and our X rotation, our up and down, to rotate the camera. So first, let's rotate our camera up and down. We just grab our X rotation and then use that to rotate the basis of our camera. This works differently than just using the rotation property. Rotating the basis adjusts the transform, which also changes its forward position. In fact, adjusting transforms can be a lot better option in a lot of scenarios, even just moving position. We can do that by setting the transform basis to a new basis from Euler, because we have a rotation value. And then we use our camera rotation that we set. Next, we do the same for our player controller, but because I really want to keep functions and code that alters node in their respective place, let's finally use our player controller script. In it, we'll create a class name and now just one function, update rotation, where we'll pass our left and right rotation and alter its transform basis like we did in the camera. Now you should be able to look around with your mouse when you run your game. Now looking around is cool, but walking is much cooler. So let's make our player walk. We're going to use the classic WASD keys to move left, right, forward, and back according to where the player is facing. Now, you could make another component like our mouse capture for an input capture, but because we're directly affecting the player controller's velocity variable, that's basically how the character body 3D node works, we're going to just add that code into our player controller script. And if you haven't already, add your 4 input maps for each direction. I've used the following labels. Our base movement script is going to take the direction of input, or which of the 4 movement keys are pressed, and then get a direction. That direction is then going to get multiplied by our base speed. In our script, we'll use the physics process function. Because we're using the character body 3D node as our base, we'll be using the built-in move and slide function, which should really be run in the physics process so that it runs with any physics interactions. We'll go ahead and run our isOnFloor check as well. So we're going to get to jumping later, but it will be nice to have gravity. We check if the player is on the floor, and if not, we adjust our velocity by adding our gravity settings times delta. You could use a number value here for gravity, but the project settings actually has a gravity setting that acts as a global value. So we can adjust that for everything. Then add a vector2 variable for our input direction, vector3 for our movement velocity, and a float for our speed value. We're going to use export variables to set default speed settings for walking and then load that into our speed variable. We set our input direction to our get vector value using each of our 4 input maps. This is just a quick way to get the full vector value of all the inputs. Next, set a current velocity of our current movement velocity. We need to distinguish between the current velocity and keep our previous velocity so we can separate out our y velocity. Then set the direction. We'll multiply the transform basis by our x and y input amounts. This will adjust our direction so that it is relative to the forward-facing direction of our player. We also need to normalize this vector so that diagonals are relative. Otherwise, you're going to be moving faster when you go diagonally. If this is a little confusing, think of a box and plot out the vector values of moving left or moving up and left. You notice how the diagonal line is longer? That's going to create a faster movement speed. So we need to normalize it. And if we have a direction or if the inputs are being pressed, we set our current velocity by lerping the current velocity to our movement direction multiplied by our speed. Our alpha value here is going to use acceleration value so that we reach our top speed gradually. Now, if there isn't any input at all, we need to go back to 0 movement. To do that, we do the move toward function to reach vector to 0 by our deceleration amount. I'm using acceleration and deceleration because I like having the players slow down faster than how they accelerate. You could just keep it the same alpha value here too if you want, but I kind of like splitting that up. You'll notice that our direction didn't have a y value, and then our current velocity is a vector 2, not a vector 3. We're in 3D space, so our actual velocity value should be a vector 3, right? Well, I've separated the y from the x and the z for a couple of reasons. One, I want to keep whatever y value we have in a frame so that it is not affected by our input lerp. When the player falls, the falling is going to happen regardless of horizontal movement, so you don't really want to mix those two. Two, I want to lerp our vector rather than lerping individual x and z floats. It does work, but doing that actually causes a weird stopping movement because the x and the z values might reach 0 at different times. So we lerp our horizontal vector and add our y velocity, and finally set our velocity to a new movement velocity. And then obviously don't forget to put your move and slide function or nothing is going to happen at all. Now, if we've done everything correctly, our player should now be able to move using the WASD keys, which is great. But we're not going to be able to do a whole lot with movement types unless we add a state machine. So in the first version of this tutorial, we created a state machine by hand using scripts and nodes. It worked fine for me until I came across the state chart plugin by the developer behind Godot. And it's honestly such a great plugin that we're going to treat it as the default state machine in this project. The good news is that it's completely free and under the MIT license, so you can get it directly from the Asset Library tab. I do recommend untagging the example folder so you don't download a bunch of unnecessary files. But once you have that installed, you also might need to restart your editor, after which you can enable the state charts plugin, and you're going to have a ton of new nodes to use for any state machine you want to create. And I want to stress too that the plugin can be used anywhere, not just your player controller. The state chart node acts as the main parent node for our system. What follows depends on the structure and complexity of the state machine you need. I start with a parallel state named root. Parallel states will allow any immediate children to run at the same time, hence the name parallel. This is different than the compound state node, which only allows one children's state to run at any given time. After our root, we're going to start with a compound state node called movement. This is going to hold our states for when we are grounded and airborne, which are two more compound states. So the logic here is that the player has two kinds of movement: grounded movement and airborne movement. They can't be both grounded and airborne at the same time, so that's separated out into compound states. More advanced state machines might include wall running or a Halo-esque grappling hook, but this is going to suffice for a basic setup. At the final level, we have what is called an atomic state, perfect to use for our first idle state. Now, like the movement state, the grounded state is a compound state because our player is going to either be idle or moving. But that also means moving is another compound state, and it's going to hold two more atomic states, walking and sprinting. I know this can get a little bit confusing, but once you understand and break down what your player should be doing and what they can't do at the same time, it starts to make more sense, I promise. It's also important to note that within state charts, compound states have a default atomic state that they go to, so that when the player enters the moving state, they're going to be in the walking state by default. So for our initial movement state machine, I've set up the following structure. You can see that once you follow the logic of how the player should move, you begin to organize the nodes to reflect that. Also, airborne is going to have a warning for now because we're going to wait on the jumping part. But we can set up our idle, walking, and sprinting states right now. One final node that you have to use is the transition node. This node is super important because it's going to set what state we should move to during an event that we can create. We're not going to worry about guards or delays right now, but know that you can create checks that must be met for the transition to occur. I like to name my transition states with the onState naming format and then match that to the event name. For example, on moving, we transition to the moving state and connect that to the onMoving event. Again, this is just a tidy organization thing. Now these events, that's how we're going to transition to new states within GDScript. We'll interact with our state machine through code using these events and the built-in signals for each state that we create. If you click on our idle states and then our signals tab, you'll notice already that it has signals for whenever we enter and exit the state, processing functions for the state, and some other signals that you can use depending on the signal timing that you need. Now, the true question is, where do you put these events and commands? This is a bit of a personal preference for me, but the plugin naturally seems to want you to use these signals and events within your specific scripts as needed. So you could have a bunch of signals sitting in your player controller and your camera controller, just like a list of signals. This is totally fine, and it does work, and it works well, but I feel it gets a bit unorganized and confusing as states add up, and then the logic gets even more advanced. My solution requires a bit more work. I feel it does a pretty good job of organizing everything so you know exactly where your state logic sits. And for me, that's what I want. I want to know exactly where I need to go to edit something or add something. So below my state chart node, I've created a parallel script node that holds scripts for each state. So rather than having a ton of processing functions in my player controller, each state holds their respective functions. I guess this is really a marriage between the old system that I did in the first version of this tutorial series and then the state chart system. And it does take a little bit more to set up, but the ability to quickly go where a specific state code is, I feel is incredibly helpful. So before we start adding our state logic, here's what we need to set up our custom script solution. We're going to start with a blank parent node named state machine. This is going to have a new script named player state machine, and it's going to hold a reference to our player controller. So when I know a reference is not going to change and we're working within the same scene, I do like to use export variables to set it and then forget it. We'll use this reference in our player controller within all of our individual state scripts. I'm going to set it here in the state machine script one time, and then I'm going to load that reference in each state when that script loads. For our state script, I'll first create a base class called state base. And this is where I'm going to set our player controller reference for all of our states. First, we get a reference to our state machine parent. I'm using the unique name feature here, so I don't have to check the parents of each state recursively. Then check if state machine exists, and then if it's a player state machine class. If true, we set our player controller to the reference that we set. Now for each new state script, we will automatically have a reference to the player controller built in, and you can add or change references as you need. I will say that I like just having all of those references within the parent player controller node and script. So let's create our idle state script. Quick note that I also have a spot for our grounded compound state within our script. So there may be code that we want to run when we're in grounded. Our idle script is going to extend our player state class. This gives us our player controller reference automatically, like we talked about. Then we select our state chart idle automatic state and then head to its signals. I want to check if we have any movement input at all. So we select the on idle state processing signal and then connect it to our idle state node. And now we can add our logic. If the player controller, and I add this just to make sure we have a player controller existing, otherwise we could potentially hit errors, and then check that the length of our input direction vector is greater than 0. If it is, we send our state chart event on moving. And yes, make a note that we have a reference to our state chart node in our player controller. Like I said earlier, being the root node of our scene, I like to hold main references in the player controller scripts. I do that by creating an export category and then export variables for our camera, state chart, collision, and believe me, we're going to have some more later on. So we'll get to that. what does that do for me? So as long as I can reference the player controller, I can reference anything. Could you use signals? Yes, but I'm not planning on making this state machine or player controller or much else of this logic modular for other scenes. It's strictly for the player. So when we do enemies, this is going to change. We're going to have different types of enemies, and so you're going to want to copy that logic so you don't have to do it for every single one. But for the player, different story. With our state chart reference set, our idle state will now move to our moving state, which defaults to our walking state whenever our input is not 0. And honestly, for now, that can be our idle state logic. Let's check that this is working first before we move on. Luckily, state charts have a great built-in debug UI that we can easily add to our scene, and we're going to take advantage of it. Within the add-on folder, look for the state chart debugger scene and add it to the player controller scene. This is going to add a UI to our 2D tab, and the only setup we need to do is to set up the initial node to watch, which is going to be our state chart node. When you run your game, you should see a 2D UI in the upper left showing your current state. Whenever we add our movement input, we shift to our walking state. Unfortunately, you're going to stay in walking forever because we haven't added any logic to go back to idle. So let's add 2 more nodes, moving state and walking state. Create scripts extending the player state class for each and then head to the moving state. We're going to add a check here to see if the player has stopped moving, and because it's in the compound moving state, it's going to run in both our walking and our sprinting states because they're children of the moving state. Hopefully you're beginning to see the usefulness of having these compound states. With our moving state active, we connect our moving state physics processing signal to our moving state script. Then check if the player controller input length equals 0. I also like to check the player's velocity too, so that the player slows a bit before immediately going to idle. If true, we send the event we created for our idle state transition. All right, now we can test our game, and when we move, we transition to walking, and when we stop, we transition to idle. And you're actually going to see this change happen in the debug UI. Adding a sprint is just as easy. It's going to happen really, really fast. Just watch. Make sure you have an atomic state for sprinting and then a transition state for it as well. Create a state script that extends player state and then make that for your sprint state. First, let's determine when we want to move into the sprint state and when we want to transition out of it. We'll use a sprint key. For me, that's going to be shift. That must be pressed to keep sprinting. In our walking script, we check if sprint is pressed, and if true, we send our onSprint event to transition. Then in our sprinting script, we check if it's not pressed, and then transition to walking. Note that we didn't use just pressed. Just pressed checks if the key was recently pressed in the frame. So this is a small distinction, but the player then could do something like jump in the air and then press shift and then immediately hit the ground and shift, because it's always checking if it has been pressed at all, not just pressed. If it was just pressed, then the player would need to press shift only after landing the jump, which it might be what you're going for, but I kind of prefer the first option. So we can now enter and exit our new sprinting state, but nothing is actually happening. We need to adjust our speed. So if we sprint, we should move faster. So we need to alter the player's speed while in the sprinting state. Now, in order to do that, we're going to actually alter how the player controller deals with speed. First, we want to create a new default speed for sprint and an export variable. Then we'll use a speed modifier to adjust our default speed depending on our movement state. If our default speed is 7 and our sprint speed modifier is 3, adding our speed modifier to our default speed will give us a new speed of 10 when we sprint. I feel this works better than just resetting our speed value because we don't have to alter our base speed. Or you could if you want to. That's a different game mechanic. We just need to set our new sprint modifier to 0, and then we'll go back to a speed of 7. And we can also do that for our crouch in a little bit. And it also means that you can combine our crouch and sprint modifiers, so you can crouch faster if you sprint while crouching, which I guess you can do. Now, when we enter our sprinting state using the state entered signal, we can set our sprint modifier to our set sprint speed. We're actually going to create a sprint function in our player controllers so that we can make other changes in the future when we sprint, like camera movement or reduce stamina. Since the player is sprinting, I like to keep that function in the player script. When we enter our walking state, we reset that sprint modifier to 0. This is going to increase our speed when we sprint, and then it's going to return back to the default when we walk, which is exactly what we want. Now we're a little bit further in this state machine stuff, so hopefully you are seeing how easy it can be to make big gameplay changes with very little work, because the state machine and the state charts, they're doing the work for us, which is really, really cool. With these 2 lines of code, we've just made our player move faster, and it took like 10 seconds. So let's go a step further and let's add that crouching state. The logic behind crouching is very similar, but there are some differences. One, you can actually crouch when you're idle or moving. So we can't just add crouch to our movement states. That's not going to work. Instead, we'll use our root parallel state and create a child for posture. That was the best word I can think of. Because whether or not we are crouching or standing is not really relevant to our movement, and it should be checked all the time. The posture state will be a compound state and have 2 atomic states and transition states, standing and crouching. Now you could also add the same logic here and add a prone if you want to do that. We're also going to mirror that in our state scripts, and we can now do our transition logic. Standing will be our default posture, and within our standing script, we'll check if the player presses the crouch key, or in my case, control. We'll also check if the player is on the floor. This is a personal choice here. You can definitely add jump crouching if you want. If true, we'll send our on crouching event to our state chart. Then we're going to do the reverse in our crouching script and check if it's not pressed and if the player is on the floor before sending the on stand event. You should be able to move between these 2 states by pressing and then releasing the crouch key already. To make our player actually crouch, we're going to need 4 things. 1, change our collision shape to match a crouched height. 2, change the height of the camera. 3, check if the player is going to hit their head if they uncrouch, then wait till they won't. And 4, change our player's speed. So first, let's set up our crouch and stand functions in our player script. These are the functions we're going to call in our state scripts. These can just be named crouch and stand. And then when we enter our standing state, we're going to run our stand function, and then when we enter crouch, we're going to run our crouch function. So already we can take care of our crouch speed. So first, we add a crouch speed modifier like we did with sprint, and a crouch modifier variable, and then add that crouch. Am I saying crotch? I keep saying crotch. Crotch modifier is a different thing. Then add that crouch modifier to our speed modifier like we did with sprint modifier. Then when we crouch, we set our crouch modifier to our crouch speed and set it to 0 when we stand. Now we move slower when we crouch and can even crouch quickly if we also hit sprint. For our collision shape, we'll actually add a brand new collision shape 3D to our scene named crouching collision. This collision shape is going to be a sphere shape 3D instead of the capsule shape that we already did, and it only needs to be 1 meter high. The idea here is that we'll simply swap between the 2 collision shapes when we crouch and when we stand. I've got references to both collision nodes in the player controller, and then I swap the crouching collision when I crouch, and then back to the standing collision when I stand. This is going to allow you to go underneath platforms 1 meter or higher, but we need to change the camera height or it's just going to look weird. That's not going to work. I'm using a single function, update camera height, in the camera controller that will run each frame. We'll check if the Y position of the camera controller is greater or equal to our crouch offset and less than or equal to our default height. Our default height position is 0.5, and we'll want our camera to go down the same 0.5 to match the new sphere crouch collision height. That makes our crouch offset 0. So as long as the camera height is between these 2 values, will move the Y position in the direction up or down, depending on whether we are crouching or whether we're standing. If we're standing, our direction would be 1, and we add our direction multiplied by our crouch speed and delta, clamping it between our low and high limits. If the direction is -1, then the height moves down until it reaches 0.0. If 1, it moves up until it reaches 0.5. Okay, now we can run this function in our 2-state scripts. In the standing script, we use our standing state physics processing signal and run our update camera height in the up direction or the 1 direction. In the crouching state, we use the crouching physics processing signal and the down direction or -1. When you run your game and you press the crouch key, the camera will gradually lower to our offset height and back to our default height when we stand. Already that's a much more convincing effect, but we have a problem if we uncrouch underneath a platform. So what can we do about that? Well, let's run a shape cast check to see if we hit our head if we uncrouch, and then to wait until our head is clear or we press crouch again. Add a new Shapecast 3D node to our player's scene. A Shapecast is like a Raycast, except it casts along a full collision shape, not just a single vector. This way we can check if the entire collision shape is free from collision before we stand up. For the shape, we're going to use the sphere shape 3D shape and set the target position to where our standing collision height would be, or 0.5 meters above. Be sure to also add a reference to the node in our player controller. The code here could not be simpler, and it's honestly thanks to the state machine. In our crouching state script, we just add a check to see if the new crouch check shapecast is not colliding. And only if it's not colliding along with our other checks can the player stand up. What I love about this solution is that even if the player lets go of the crouch key, they're not going to stand up, but they'll automatically stand once they have open space above them if they keep it unpressed. Now, before we jump into our jump state, let's check out a really cool feature of the State Charts plugin, the ability to add your own debug expressions in the Debug UI. Let's say we wanted to check what the player's current velocity was and whether the crouch check was colliding, and have that show in our Debug UI. You can add this code anywhere, but I like adding it to the state machine script so it's all in one place. Again, organization, tidiness. Nothing worse than having a debug or a print code that you can't find and it just keeps printing. I hate that. It's terrible. In our process function, we're going to check if the player controller exists and then access the state chart and then run the set expression property function. This function allows us to set a string and a value to monitor it in the Debug UI like we're monitoring our current state. I've added a player velocity property that monitors the velocity value and a player hitting head property that passes the crouch check is colliding Boolean. When you run your game, you should now see those two properties and their values update live. If you can't, you might need to make your UI debug taller. Just a really quick and easy way to check on values when you're testing. Adding the jump state is actually easier than the crouching state. So we already have to deal with the Y value in the player controller, and in the future we're going to cover more advanced jumping like double jumps and coyote jumps, but they're all going to be based on this setup. We can finally use the airborne compound state, which will honestly, it's still going to be unhappy with you. So just ignore that little warning sign. Even after you add a jumping atomic state and an on-grounded transition node, just don't forget to add an on airborne transition in the moving compound state. Truthfully, the order here doesn't matter, but I do feel that it helps with the organization, tidiness. This time, let's create our jump logic first, and then we're going to connect our states, just a different way to do it. In our player controller script, I've added a jump settings category and a jump velocity export variable set to 5. You can alter that depending on what kind of jump you want to have, how high you want it to be. We already have our player falling with gravity when they're off the ground. We just need to send them up. So create a new jump function that adds our jump velocity to our current y velocity. Then in our grounded state, we connect our grounded physics processing function and check if the player just pressed our jump key and if the player is on the floor. If true, we run our jump function and then send an onAirborne event for our transition node. This sends the player in the air into our airborne transition state where we run our airborne state physics processing signal and check if the player is back on the floor. If true, then we send our grounded event. You should be able to jump now and then swap between these two states. You're going to see that in your debug UI. We have one more check to run though, since we can also become airborne without jumping if you just, yeet off the ledge. So back in our grounded script, we check if the player is ever not on the floor. And if it is, then they must be airborne. So we transition to airborne. As we add more complex jump mechanics, this logic is going to change. It just will. But this works for a basic jump state and it will easily adjust later because how organized our code is so far. All right, we're going to move away from our movement state machine now, and we're going to focus on the staple of the FPS genre, the crosshair. But in order to do that, we need a basic UI setup. And to do that, we should create what is called our game's main scene. I actually have a video on this that goes in detail of why a main scene is so important, but for now, it's a great foundation for your game's structure. The main scene is going to do a couple of things. First, hold, load, and change our levels or 3D scenes, and then hold our user interface. The main scene is basically going to be the scene your game loads first and keeps open, only loading and then managing children's scenes to swap between levels and UI elements. That's really oversimplified, but we're going to jump into specific loading and saving and swapping levels when we get to scene management within this series. Now, for our purposes, we just want to create it so we can start our UI. I like to structure the main scene like this. There's a parent node that will eventually hold an Omni manager script, a manager node and children that will hold different mechanic-specific manager scripts, and then a node 3D for the current 3D level, and a canvas node for our user interface. Our user interface can be its own scene as well so that it's easier to navigate. The user interface scene will hold our different control components that make our UI. Eventually, we'll manage what is visible when, but for now, we're focusing on one component, the reticle or our crosshair. We'll create a center container component named Reticle. That should be anchored as a full rect within that anchor setting. That's going to center our crosshair and our reticle draw control node that will house our script. Now the crosshair design can vary and you can just put a plain image if you want to, and then I guess you're done. For this project, we're going to create a dynamic circle reticle that you can customize. For our reticle draw script, we want this to be a tool script so that we can see it update in the editor. That's going to be really handy. I also have a video covering the draw function, which is really vital to what we're going to be using here. So if you're curious about it, you can check that out in the description. Basically, there are built-in functions for 2D based nodes in Godot that allow us to manually draw lines, curves, and other things through code. We're going to be drawing 4 line arcs that can change in size, thickness, and color. We create 5 export variables for our different options in a custom function draw circle crosshair. The gap angle determines the size of the gaps within the reticle, but we're using degrees in our export since that's more readable for me. But we actually need radian, so we convert that for the gap radian value. Then we create the line arc segment using our gap radius and pi. This will create 4 quadrants of line arcs. For each line arc in our arc segments array, we find the start of the angle and then the end of the angle, finding points between the two depending on how many segments we want to have. For loop creates a series of points based on that information that we then feed into the draw polyline function, setting our line color and thickness and whether it should be anti-aliased. We can also add some future-proofing functions that will let us adjust the reticle or crosshair externally. If, say, you want to change the color or thickness for a new gun, or if the player hits an enemy. To adjust the reticle in the editor, in addition to the tool line, we also need to add a setter in our export variables so that we redraw our lines after we make a change. You can do that by using the set and then the callable for our respective update functions. Within the 2D Editor tab with the main scene active, you should be able to adjust your export variables and see the changes live. If you run your game, the reticle should be active and centered on your screen. Now the crosshair doesn't actually do anything. So we're going to use a raycast from the camera to detect what the player is looking at given a certain interaction distance. This is really a basic setup for user interaction with the environment, and it's going to be something that we're going to build on heavily in future videos. So for now, we're just going to print what object the player is looking at within 3 meters. In our player controller, we'll create a new Raycast 3D node, this time as a child of our camera 3D node. This raycast will extend from the center of our camera in the forward direction for 3 meters. Do note that the 3 is negative here because forward Z is negative in the Godot engine. We'll create a new interaction raycast script that will simply detect what object the raycast first collides with within our parameters. Within the process function, we check if colliding, and if true, we set object to our getCollider function, which returns the first object the ray intersects. Now, because this runs every single frame, we can check if the detected object is the same that we already detected in the last frame. And if so, just return. If not, then we set our current object to the new object. And if we don't detect anything at all, then our current object is null. And that's it. In the player controller, we add a reference to the Raycast node and then add a new state machine debug to show what our player is looking at within our 3 meter distance. This is incredibly simple, but it's going to be the base of any environment interaction we want to add going forward. Finally, I wanted to add a few more lines of code for some quality of life changes moving forward. And that's just a way for us to quickly exit and reload our game. Remember, we had our managers node in our main scene. Let's add a new node, game manager, and then a new script. Within it, we'll use an unhandled input function to check if we press 2 new inputs, dev exit and dev reload. For me, it's a great way to speed up testing. You can exit the scene by pressing escape or reload the scene by pressing F1. All right, so that's as far as we're going to go in this very first video, but I feel it should provide a really solid foundation for a ton of great FPS mechanics that we're going to cover very soon. Again, you can just download this finished starter project for free on my website. Just sign up for a free account and you can download and use the project however you want. Every new video in the series will be covered in full on this channel, with the source files being immediately available to paid supporters as they have been. Now, if you're already a supporter on Patreon, the files will still be uploaded there in addition to my new website for the next year. So that's 365 days worth of videos that will still go on to Patreon. I'm moving away from Patreon to a different platform as of now. So my site is going to have even more resources and features moving forward, and it should also be cheaper for you and for myself. So if you're able to swap over to the website from Patreon, I encourage you to do that. But again, nothing is going to change for Patreon for the next year. So you're not going to get left out. Additionally, we're focusing on the FPS genre because I am, for reals, making a retro FPS game myself. Devlogs for that are going to drop really, really soon. And while the Steam page is not quite ready yet for wishlisting, if you have any interest in my game, Children of Kronos, do check out the link in the description to be notified of the Steam page launch and any news regarding development. I'm really, really excited to start showing you what I've been working on, and equally looking to get feedback from you as soon as possible. Finally, a little more info on why this video even exists. How is version 2 of this FPS series going to be different? Well, one, I really wanted to step up the production value, and the quality of the series. The short and quick videos were easier to make, but I felt they sped by the actual learning part and just became more show and tell. Also, version 2 will have more modular videos added to the series. New features will be more comprehensive and easier to add to your own projects without having to go through every single video in this series. I'm viewing this series sort of like this. We're going to start with a large base FPS project, which is this video. This will have more foundational parts that we can build upon in the future videos. Those future videos are going to be longer, much longer. No more 3-minute tutorials. For example, instead of doing 10 videos on adding weapons in an FPS, there will be one long video called a branch that will cover most of the foundational parts of weapons like ammo and movement, weapon switching, etc. These branches will be directly connected to the base FPS project as much as possible. This means you shouldn't need to watch every single tutorial to get the most of new videos, and it should be easier to implement parts of the tutorial series in your own project, even if you're not working with the same base code. We're also going to dive into the use of Trenchbroom in making your own FPS game. If you're not familiar, Trenchbroom is an awesome level editor for Quake and provides an amazing structure to make levels really, really fast. The goal of this series is to share what I've learned going through the process of creating my own FPS game so that you guys have even the smallest head start in making one too. Thank you to the supporters on Patreon and your patience. You truly, truly make it possible for me to spend time on making hour-long videos. Again, the project source files for this and future videos are on my website. If this video was helpful, consider becoming a member to support the series. I have a small roadmap detailing the topics of future videos. Videos will come a little slower than the 1 or 2 every week that I used to do, but they're going to have way, way, way more information. So thank you so much for watching the weeklies and just being so supportive. I'm going to catch you in the next one. And until then, keep creating.